started modeling our LTI system using differential equations and difference equations. We started our continuous system first with differential equations, and we categorized our response into two different responses. We call it zero state response and zero input response, and illustrated how we can determine those responses from the input output relationship of a system. Now, as you know that in determining the zero state response, we have two techniques to do that. We can use differential equation solution directly, or we can use convolution. If you want to use convolution technique, you need to know the impulse response of your system. Now we will show you from this time ahead how to determine the impulse response of a continuous time LTI system from its input output relationship. And our assumption is we are dealing with single output and single input systems. Although some mathematical rigors are there, but we will be avoiding those rigors. You try to understand the shortcut technique, how can we determine the impulse response of a system analytically. The reason behind this is what practically actually it is very difficult to find the impulse responses, but still we have some technique. We can do that if we have a transient oscilloscope that can record or store data quickly, then you can apply a very momentary input to your system, then record the output. That can be considered as your impulse response for your further study. Now, you know that we have a general form of input-output relationship. You can write your relationship in many different forms. This is one of the forms. In your Haykin's book, you may have your different form, but you can easily compare this equation with that one. You will see that those equations are very similar. Now, in order to represent the system in a shorter form, we have to use the operator algebra to do that. So you know your operator algebra from your mathematics course. Your D is your differential operator, okay? The exponent over D denotes the order of your differentiation. So as a result, in your output side, you will have a polynomial of D, and your input side, you will have a polynomial of D again. But the coefficients of those polynomials will be different. Another issue is that that polynomial is the polynomial of operators, not the polynomial of any independent variable or something like this. So in this sense, you have to consider this thing. Those equations will be meaningful only when they can be associated with some variables, and we can operate the variables by these operators. Now, in the short form, your input output side operator is okay, I extracted this lecture from B.P. Lathi's book. So this is your in output side operator QD, and this is our input side operator PD. Both are polynomials of operators. Now the definition of impulse response will take this form. Okay, you will see that your impulse response may contain an impulse. Have we discussed that thing earlier, that when an impulse response can contain an impulse?
No, sir.
I don't know whether I discuss or then I will again do that. But if we want to, for example, extract our input from the output at the output end of a system, what must be the nature of the impulse response? Okay, in order to discuss the thing, that I need to go to just I need to share your whiteboard. Okay, by your common sense, you can see that if we have a system and your system response is HT, you are giving an input, say XT, at your output, you want to find your XT. Then what will be the nature of your HT? Your HT must be a delta T, isn't it?
Yes, sir.
In general, when we expect the exact form of the output after having this input, after having the input processed by your system, then your impulse response should be equal to the impulse, like an impulse. Otherwise, exact reproduction will not be possible. But not always that this system will say that your system will have the impulse response that is also an impulse. But we may have our system depending on the location from where you are extracting the output, that will tell you the nature of your impulse response. Okay, we illustrated the thing by using a simple rudimentary example using an RC circuit. I am repeating this thing probably several times. Okay, if we have and already you have your control course with you, then you know this thing. That, for example, if we take the output from output of the voltage as the voltage across the capacitor as your output, by using your Laplace transform, you can easily say find that your ST has the form 1 divided by RC to the power minus T by RC UT. Didn't we show this thing earlier?
Yes, sir.
Yes, sir.
If we have shown this thing earlier, this is what if we take output across your capacitor. But if we take the output across the resistor, what will be your transfer impulse response, HT? Because depending on the location of our output, your impulse response will be determined accordingly. By using your Laplace transform, you can easily find that the transfer function of this system HS, if we take voltage across your resistor as the output, will simply be equal to what? It will be equal to R divided by what?
R plus 1 by CS.
R divided by R plus 1 divided by CS, isn't it?
Yes, sir.
And it will be equal to what? RCS divided
1 plus
by
RCS.
RCS plus 1. What is the Laplace inverse of this quantity? What will be the what is your HT by taking the Laplace inverse of HS? Consider, okay, for simple case, say RC equal to 1. Then this factor would be equal to what?
Cos t.
S divided by S plus 1. What is the Laplace inverse of S divided by S plus 1?
Sir, t e to the power minus t.
Sorry?
Sir, t multiplied by e to the power minus t.
T multiplied by e to the power t. Okay. Did you find it or simply memorized it from your, wrongly memorized it from your earlier classes? Did you find it by yourself? That Laplace inverse of S divided by S plus 1 is equal to what?
Sir, we need to do partial fractions.
How many, for example, hours you need to partial fraction it? Is it not something like this 1 minus 1 divided by S plus 1? A primary school student
Yes,
can
sir.
do that.
Yes, sir.
Then what is the Laplace inverse of this thing? Is it not equal to delta t minus e to the power minus t ut?
Yes, sir.
Okay, please be careful about your identity. Okay, you are a third year student. Be careful about that. So you can easily see that this type of system, depending on the location of your output, your impulse response may contain an impulse. Another way of thinking this thing is that whenever we get S in the Laplace transform, for example, if this is the transfer function, I don't know to what extent you have analyzed your transfer function. I don't know exactly. Your transfer function will have a numerator polynomial and will have a denominator polynomial. If the order of your numerator polynomial and denominator polynomial are same, then what will happen? In your Laplace inverse, a delta function will appear. Isn't it? In this particular example, what is the order of your NS?
So 1.
জোর করে কথা কও, শোনা যায় না।
1, sir.
1, sir.
And what is the order of your second?
Sir, 1.
Okay, just hold a minute, please, because Vice Chancellor phoned me. Okay, sorry, I had to attend the phone call from the Vice Chancellor. Okay,
sir.
then what is the order of your numerator?
1.
1. And the order of your denominator is?
1.
So when the order of your denominator and numerator will be equal to 1, then what will happen? If you partial fraction it, then a constant term will be there, isn't it?
Yes, sir.
Yes, sir.
And that constant term results in, that constant term in ACS will result in an impulse, okay? So that is what the logic why. When the order, for example, of your derivative of your input side and output side will be same, then an impulse might occur in your impulse response. So having this thing with us, then let us start with the general form. Okay, the general form of the impulse response can be written in this way. Your Bn delta t plus Pd Yn t ut. Then what are the things that you need to know? Let us start with. Your Bn is the highest coefficient or nth order coefficient of your input side. If you examine your Dn, Pn, you will see that the coefficient of Dn in the input side is Bn. Thus your Bn would be there. If your Bn has no Bn, then that term will not be present. Okay. Another issue is what is your Yn? Yn is the natural solution of your differential equation in generalized form. Natural solution means your homogeneous solutions. So when our differential equation will be available with us in the operator form, you can write it QD QD YT. This is what your output side. Then when we set this side equal to 0, then this solution will give you YNT. Now you see that in YNT, the form of YNT is simply exponential, for example, of this form, and it will, depending on the order, it will contain some integrating constant to be determined. So in our earlier cases, we determined this integrating constant in two different ways. When we find ZIR, we applied initial conditions to find the constants. And when we applied the complete solution, then we applied the initial conditions after adding the particular integral with it. But here in this case, in determining your HT, after obtaining your Yn, what you need to do, you have to operate your Yn by PD in this way. Once this operation is made, then we have to apply our boundary condition. Those initial conditions are the auxiliary initial conditions defined in this way. Because you see that transfer function is determined for 0 state response only. Transfer function cannot be determined for 0 input response, because if you do not have any input, there is no any question of transfer function and no question of impulse response. For this reason, your impulse response always refer to the system that is has no state. That means no initial values in it. So the artificial auxiliary initial conditions will be something like this. Yn, this is how this n stands for your natural response, and the superscript is the order. So this is what the derivative of your Yn, one order less than the actual order. At time t equal to 0 would be equal to 1, and the rest of your initial values will be equal to 0. So in this, by using these auxiliary initial conditions, we can find the associated integrating constant present in your Yn. We will be illustrating the technique by using an example, then it will be clear to you. This is not a very difficult deal. Whatever method we have learned so far can be applied there to find the initial or the impulse response of your system. Let us go to the next slide. Okay, refer to our earlier example. If we okay, if we consider our earlier example, the example was in terms of differential equation, that was something like this: d2 plus 3d plus 2 equal to twice x. You can easily say that your QD equal to d2 plus 3d plus 2, and your PD has a constant only. If we apply the thing there, then you can easily see that what is the order of our differential equation, because you have your highest operator d2, so the order is 2, isn't it?
Order. Yes, sir.
In the input side, no, in the output side. Okay, but in your input side, there is no any derivative. So as a result, your b n equal to b2 is equal to 0, as b1 is also equal to 0, and only b0 is existing. As a result, your pd is a constant equal to 2, and your n equal to 2 or bn equal to b2 equal to 0. So in this case, the impulse response will not contain delta. Now next step is what? Next step is we have to find ynt. We have already find ynt, where ynt is equal to c1 e to the power minus t plus c2 e to the power minus 2t. As we had our two characteristic root, one was equal to -1, another was equal to -2. Now once we have this thing with us, our auxiliary initial conditions are one derivative less than the order of your system will be equal to 1 at t equal to 0, and the other will be equal to 0. So having this thing applied to ynt, you see that if we set ynt yn equal to 0, it will be 0. So this is what this equation. And if we take derivative once, then set time t equal to 0, equate it with equal to 1. Then if we take the derivative of yn, what is it? What is the derivative of yn? dyn prime t equal to what? Is it
Minus
not
C1
equal
e
to
to the power
minus
minus t
c1 e to the power minus t minus c2
minus
e to the power
2c2 e to the power minus 2t.
minus t. So if we set t equal to 0, then this is what this equation, and set it equal to 1. Then we will obtain two equations there, solve simultaneously to find the value of C1 and C2. Once you C1 and C2 are available, then this is your YNT. Now once your YNT available, you apply this YNT to our original equation of HT. So you see that your HT was equal to Bn delta T plus PD into YNT UT. So in our case, our B2 equal to 0, so 0 delta T. In the second case, PD equal to 2, so it is 2, YNT is this is UT. Now, if a derivative term exists in PD, then you have to operate your YNT accordingly. For example, say, if our PD is equal to something like this, say your PD is equal to, say, D1 or D plus 2, then if our PD equal to D plus 2, then if we want to operate, for example, our YN with PD, then what will be the value? Your PD equal to D plus 2, and you have to operate it with Yn. Is it not equal to dyn dt plus 2yn?
Yes, sir.
So in this way, you have to find your this term, okay? In this real example, as we are our PD equal to 2, we did not take any derivative of yn, but if your d term is there, then you have to take the derivative and put your derivative accordingly. So in this way, you can find the impulse response of your system. So once the impulse response of your system is known to you, then your ZSR can be determined by convolving your ST with the input XT. So in our earlier example, our input was equal to an exponentially decaying function. And here we obtain our ST this. Then you can use your convolution equation there to find your SR, and this is what your ZSR. Then we have found ZIR earlier. Then if we add these two terms together, then this is what your complete solution. You can easily compare this complete solution or output with the output we determined earlier by using other techniques. So if you want to summarize this technique, what is your what will be the summary? Okay, you have to write your input output equation. Then that will tell you what is the order of the polynomial of your input side and what is the order of your polynomial in the output side. Once you have written your differential equation into polynomial form, then you obtain your homogeneous solution. Do not put any real boundary condition there, initial condition there, but you have to use the initial condition that one derivative less than the order of your system at time t equal to 0 would be equal to 1, and all other initial values will be equal to 0. Then having this initial values applied to your yn, you will find the integrating constant, then your yn will be determined. After having your yn determined, then you put your solution to the generalized equation of HT. Your HT equal to Bn delta T plus PD into Ynt ut. Whether your delta n will exist or not, this will depend on the order of the polynomial of your input side. And already you have learned that the impulse response of a system that is also related to transfer function will contain an impulse only when the order of your input side derivative and output side derivative will be same. If they are not same, usually the input derivative will be less than the output derivative, order of output derivative. So your impulse will not be available in the impulse response. And from your polynomial type or Laplace transform perspective, you understood this thing, okay? If the order of the numerator polynomial and denominator polynomial of your H's will be same, then what will happen? There will be an impulse in the impulse response. Now you see that, okay, in your control engineering, what you are learning, we have some standard form of writing the transfer function of a second order system, because the transfer function of a second order system is taken as a very ideal case of analyzing the higher order system. The transient behavior of a second order system is very important in control engineering, from where few parameters of transient response are usually extracted and used to standardize the design of a particular system. Can you tell me what are the parameters of a second order system that you need to study in control engineering?
Sir, damping ratio.
Damping
and
ratio, yes, very
natural
good.
frequency.
Damping ratio, natural frequency, rise time, settling time, steady state error,
Peak time.
and
Overshoot.
the peak.
Percent overshoot.
Okay, that all other the thing related to what? Are not those things related to transient response?
Yes, sir.
All these things are related to transient response, okay? If we give a step input to our system, your step response of your system can have this type of nature, okay? It will rise or something like this, okay? That depending on this rise time, you have a rise time definition, rise time.
Yes, sir. 0.1 to 0.9.
Okay, yes, rise time definition. You have a settling time definition. Settling time definition. You have an overshoot definition. You have an undershoot definition. You have an steady state error. I hope you have already learned this thing, okay?
Sir, what is undershoot?
Undershoot means when you have a transient response. Okay, what is when that type of response will occur? If we have a
In
step,
an overdamped.
yes, you may have, for example, a system response then can go in this way, okay? So an undershoot will be there from a specific level. That is also a parameter to be understood. Overshoot means from a set value, you have to calculate the overshoot. Similarly, from a set value, you have to calculate how down you can go from that value. Okay, in this way, the overshoot and undershoot should be specified. So these things are there. If you have a higher order system, you have you can approximate those higher order system by using this system. As a result, we have a standard way of writing a second order system. Okay, I hope you have already learned about it. So if you want to write those equations, the equation in a standard form, the characteristic equation will of a second order system will take this form. I hope you are accustomed to the symbols.
Yes, sir.
Don't you know this thing? In a
Yes,
Laplace
sir.
transform, your lambda will be replaced by S. As simple as this. Here, this zeta is what? It is the damping ratio. Omega is omega
Natural
n.
frequency.
Omega n is called undamped natural frequency. Undamped natural.
Frequency.
This is what the very important issue of a system. Okay, that will determine if your response become underdamped, then how much time it will take. For example, what will be the frequency and how much time it will take. That the combination of these two things will be needed to understand this thing. Okay, you zeta and omega n. And in an RLC circuit, you can easily find this thing. Can you find this thing for an RLC circuit?
Yes,
Okay,
sir.
try to explore it by your own. Okay, although we represent the thing in this way, in the generalized mathematical form, you can also write the thing in this way. Then you can make a correspondence that what is the value of zeta and what is the value of your omega n. Actually, this is also related to the root of your characteristic equation. If we have two roots there, lambda 1 and lambda 2, these are the two roots, and those two roots can be written in this form. And you can easily see that we have a real part negative, and that negative real part signifies that it is a stable system and passive. Active system can be also have your real part negative if we can operate it in the stable region. Now that alpha will contain something that is related to damping, and your omega n, the imaginary part of your complex root, this is what your natural frequency. And that natural frequency can exist or may not exist. If your system is damped, critically damped or over damped, then the root lambda 1 and lambda 2 will be real and unequal, or it may be equal. But in all the cases, there will be no any damping undamped frequency. So your system will be over damped or critically damped. But if your system will contain both your damping factor and omega n, then we call the system what? Underdamped, isn't it? Most of the real systems are what belongs to which category?
Underdamped.
Most of your system belongs to underdamped category. Okay. And so these are the things, you know, this thing, try to relate those things with your control engineering in system and circuit signals. We also need this thing to characterize our system, because control engineering is also a part of our study. And you can easily plot this thing by using your MATLAB. Okay, if we plot the for a particular system with your alpha is greater than omega n, what does it mean? It means that your system doesn't contain any natural frequency, in fact. So you can easily see that your responses are damped type, isn't it?
Yes, sir.
Then another issue is that if it is critically damped, then your damping nature will be damping, but a bit different from your over damped system. If we have our system that is underdamped, the response can be something like this. Look, this is can be your step response. It depends on the from where you are taking your output. Okay, can you imagine that if we have an RLC series circuit, from where we are taking output by examining this response?
Sir, from the capacitor.
From the capacitor. Okay, what type of output then if it is capacitor?
Voltage.
Because in your capacitor voltage can be your output, your capacitor current can be output. If it
Sir,
is
voltage.
is it voltage? You guys, this is not the problem. Okay, without examining anything, you just give a response. This is not good. Hey, if you have a capacitor and your input is a step, then in the steady state, what will be the value?
So it will be input
Yes.
voltage at the steady state.
Sorry? What will be the value of your output at the steady state?
As the input voltage.
Is that this is true here?
No, sir.
No, sir.
Okay, what type of input is the response is this?
Undamped response.
Okay, you know this thing, try to explore on top of it, okay?
Yes, sir.
And I hope you have already learned how to solve your differential equation by using MATLAB, okay? You have your numerical algorithm, you can use them, or even your Laplace has a symbolic mathematical toolbox. Have you learned about it?
Yes, sir.
That in the way you solve your differential equation by pencil and paper analytically can also be done by using your MATLAB. This is called symbolic toolbox, MATLAB toolbox. Okay, you can apply these equations there in your symbolic toolbox and verify it. So this is what our system. Now I will talk about, although you learned this thing from your control engineering meanwhile probably, but I will recap the thing. It can also be without Laplace transform in time domain, that also can be examined. You know that if we have our characteristic equation, that characteristic equation comes from the homogeneous part of your differential equation, actually represent the whole system. Your characteristic equation represent your whole system. As a result, what will happen if we know the nature of the roots of our characteristic system equation, that will tell you the whether your system is stable, marginally stable, or not stable. Okay, but we will be giving a simple hint here. More elaborate discussion you will have in your control engineering. Okay, that's why you see that in general in your control engineering we use a plot, we call it pole zero diagram, isn't it?
Yes, sir.
Your pole zero diagram is a vital diagram in the complex plane in understanding the stability of, or even from your pole zero diagram, you can extract the transfer function of your system also. Okay, you will find many applications of pole zero diagram in control engineering, starting from determination of transfer function to investigate the stability of a design system, and even you can tune or the locations of the poles and zeros by tuning some of the parameters of your system, so that you can ensure that your system will be operating in the stable region. So you have already learned that transient response is the fact of a system is the basic thing. Okay, where you will find the characteristic root of your system as appearing as exponent of an exponential function. And if the exponent of an exponential function is purely imaginary, then it will be giving you a sustainable oscillation. That means undamped type response. But such systems are sometimes called marginally stable. The reason is that by some way or other, if a real part is coming, no matter how small it is, if it is positive and rise in the left half plane, then what will happen? the response of your system will grow. For example, if we have our root lying in the imaginary axis, then what type of system will be?
Undamped.
Undamped, and this is marginally stable. Why we call marginally stable? Because the response will contain this term e to the power plus minus say omega nt. But if somewhere or other this any one of these pole is disturbed, it is going in this side, no matter how small is it, what will happen? Say in this case, what will happen? Say a very small delta part is added with your j omega n, and you are multiplying with t, your delta is positive. Then what will happen?
It will grow exponentially.
That means it will grow indefinitely with time. So your system is unstable. So if your root lies on the imaginary axis, your system is marginally stable and it is vulnerable to instability. Okay. Now, if any root lies, for example, in the left right half plane, then what will happen? Your system is unstable. And if we have our root lies in the left half plane, our system is stable. Okay, so by using this simple analysis, you can have an estimate about the stability of a simple system, but you need further analysis using some advanced method to investigate the stability of a system. That is what the content of one or two chapters of your control engineering theory. Okay.
Yes, sir.
So this is how the few problems from your book, you can solve them just to get accustomed to the system. Now with this thing, we'll be going to our discrete time cases. Okay, I will be leaving this thing to you to be understood by yourself, how to find the initial values of a system if the state of your system is described. Okay, you consult with your previously learned text, then try to understand how initial values can be extracted from the definition of a circuit. Okay. So that's it from our continuous system part. Then let us start with our discrete type system. Okay. You see that your discrete type system has also a similar type of input-output relationship, but those input-output relationships are determined by using what type of equation? Let me open up the file. Do you know what equation we use to represent our discrete time system?
No, sir.
Is it not your difference equation? Difference equation. Did we discuss it at the beginning of the chapter that we have our two general form of input-output relationship? One is for continuous time system, another is for
Discrete.
okay. Can you see this slide?
Yes, sir.
Okay, this is your DT LTI system difference equations. Okay. In your Haykins book, those things are also written there. Okay, you can compare this equation with the equation written in this book. I have taken this from your BP Lathi's book, and I found that the presentation of this thing there is a bit systematic, and it is not very difficult to compare the presentation with those of your Haykin's book. Very simple. What we have seen there, you know that a differential coefficient in the discrete domain can be represented by differences, isn't it? Because we know that if we make the difference of two successive samples of a discrete time system, it will represent a differential
Differentiation.
coefficient. So as a result, the input-output relationship of a discrete time system can be written in the form of difference equation. And if we write the equation in a generalized form, it will take this form. That representation is very similar to the representation of continuous time derivative. So you see that here n represent the order of your difference equation. Now we have two ways to write those equations actually. You see that y represent our output, yn, and xn represent our input at the present time. When we change the index n, or if we make, for example, yn plus 1, it means that we are advancing in by a order equal to n, and if we subtract it, we are simply delaying it. But in both ways we can go. Very similar to you taking difference by using forward difference or by using backward difference. Have not you learned the thing earlier?
Yes, sir.
The forward difference and backward difference. We have also another difference algorithm. What is the name of this difference algorithm?
Central divided difference.
Central divided difference. Okay. Why we need that three types of differences?
Sir, for the increase in the efficiency in our numerical system.
Very general statement. Have you examined it? Which algorithm is more efficient than what? Is
Yes,
it
sir.
unique
The central divided difference is better.
for all system? What is the criteria that for selecting it? Then if it is the best one, then why we study the others?
So its accuracy is higher than forward and
Okay,
backward.
try to study this thing. If one algorithm is enough, then we do not need many, because it is also problem specific. Or type of problem you have to study first, that in which type of problem, what type of algorithm is suitable. Now you see that your first equation is advanced operator form, second equation is delayed operator form. We can commute between these two by simply replacing n plus capital N by n. Then we can easily obtain this equation, okay? Our objective is what? In your differential equation, our objective was to find the output. We solve for output yn, yt. In your discrete domain, our objective is also to find yn. Okay, yn, but in the case of a continuous time system, it is continuous. If analytical solution is available, then we can solve yt analytically. If the analytical solution is not available, we can solve the equations numerically. In the same way, we have our two different ways to find yn. Yn can be solved by using recursion. How do you know what do you mean by recursion or recursive formula?
Yes, sir.
Okay, then you know it. Okay, that means the results of your previous calculation will be used to calculate the present values, isn't it? So in this way you can go. That recursion or recursive calculation of yn can be easily be understood. For example, if we want to solve this equation for yn, can we rearrange the equation? You keep your yn in one side and put all other things to the other side. Okay? Then you put your n equal to 1 first, then calculate the value for, say, put n equal to 0, calculate y0, put n equal to 1, calculate y1, put n equal to 2, calculate y2. In this way, you can keep going on calculating this thing. We have also illustrated this thing at the beginning of the chapter. when we illustrated convolution, something like this. Thus, in this way, you will see that if we want to find y0, in this equation, if we put y0, and that will be equal to what? Y minus 1. And in the same way, another term may come here with y minus 2. In this way, you can go there. That means in order to find the value of y0, you will need 1 by y minus 1, y minus 2, and so on. Isn't it?
Yes, sir.
Then
Yes,
if
sir.
you want to calculate y0, then you will need y1, you will need y0 that you have calculated earlier. Similarly, if we want to calculate y2, we will need y1 that we have calculated earlier. In this way, you can keep going on calculating yn for each value of n. Then, but the condition is here is that this will not be efficient. The reason is that if you want to calculate many iterations there, then it will take time to calculate. Even in many of the cases, it will not converge. That can be used, for example, for a system with few samples of input, and your system is stable, so that after calculating few output, you will see that your output will not be appearing. So it can be efficient there. You can solve it manually. Even you can write few lines of computer program to calculate for your output. But in general, what we can do, if we have our generalized system, we have our two different techniques to solve. Okay, in your continuous case, how many techniques we have? We have our analytical technique. Analytical technique means by using the technique of solving differential equation, we can use those techniques to find the solution for our input of relationship. Or if analytical solution is not available, we can use numerical solutions. But the equations whose analytical solution is available, you have your two different methods to solve. One is you can use your time domain technique that we illustrated, and you can also apply your transform technique like Laplace transform to solve your differential equation. I hope you know this thing. Laplace transform can also be used to solve what? Your differential equation, okay? In the same way, we have our three different techniques in our difference equation. You can use recursively that I have illustrated. And second thing is you can obtain analytical solution. Analytical solution can also be obtained. Analytical, recursive, again some. Okay, we will have our analytical solutions or recursive. Then, like your transform technique, we have another transformation technique by which you can solve your difference equation, that is called Z transform. Have you heard about it?
Yes, sir.
Z transform is the discrete version of Laplace transform. It will be the central content of your DSP in your fourth year. Now let us start with representing the thing, okay? This example illustrates the recursive solution. Consider that we have, okay, in this book, that K is similar to N of your Huygens book. This lowercase k is similar to your Huygens book, and F is used as your input, that is equal to X. So if we replace our F by X, the input, and K by N, then those equations will be similar to your Huygens equation, okay? Now, in which form our equation is written, it is in the advanced operator form, okay? You can convert it into delayed operator by simply replacing your K equal to K by K plus 2, okay? If we replace your K by K plus 2, then we can easily change this equation to delayed operator form. Now, if you want to solve it for our if you want to solve it by using recursive formula, then you see that your output is yk. In this yk or equivalently equal to yn. And what you need to do, you have to make a plot. For example, this is your axis k or n, whatever it may be. Then you calculate the value, say at k equal to 0, calculate the value at k equal to 1, and so on. So then if we keep going on calculating the value of your output for different values of k, you will be obtaining the solution in the recursive way. So this process is illustrated in this example. So you see that when we want to find k equal to 0, then you have to set, if you want to find the output at k equal to 0, then in this equation, if you set k equal to -2, that will give you y0. So then your y0 would be equal to this. Okay, from where we are getting this value? If, in order to calculate this value, you will need the value of y -1, you will need the value of y -2, f0, and f -1. All these values are already given because your fk is given as k, starting at k equal to 0. The if your input is starting at k equal to 0, and if we set k equal to -2 in equation 9.5, you will see that you will need a value of f that is equal to f -1. And your input is not there because your input starts from k equal to 0. So your f -1 would be equal to 0. So if we put this value there, you will obtain your y0. Then you put k equal to -1 there, that you will obtain k1. Then k1 would be equal to this. In this way, you can calculate the other values of your y, and that can give you the solution for this differential difference equation. This is what your recursive technique, and it is very simple. Even by using your computer, you can write a single loop there that will give you this recursive operation. Now we will be proceeding in finding some way of solving the equation analytically. In order to do that, although this technique is, I found it very easier to understand. For this reason, I am illustrating this thing to you. But you can also follow the technique for Haykin's book. They are exactly same. Now you see, we use the operator algebra here. We use the operator for representing our derivative. We can also use operator here to represent our difference. Those difference operator here in this book is represented by E operator. Consider that if we operate, for example, your E operator will have an exponent, for example, say x. The x exponents will tell you if it is positive, it is advanced operator system, and if it is negative, it is delayed operator. And that will represent the order of your system, or how many samples it will be advanced or delayed. For example, if it is E, that means it is advancing one sample. If we use E -1, it is delaying one sample. So when a function say fk, the input function is operated by E, then what will happen? The exponent is 1, so it will be advanced by one sample. Similarly, if it is 2, it will be advanced by 2 samples. If it is n, then it will be advanced by n samples. So in this way, if we want to represent our difference equations, say consider this is our input-output relationship of a fictitious system. If we have this system with us, then this system will give you the input-output relationship. Then we can write this system using our operator notation. You see that we have our yk2 there, yk2. Yk2 means what? Yk2 means if we operate our yk by E2, is it not equal to yk plus 2?
Yes, sir.
Yes, sir.
Okay, in this way, you can replace your yk plus 1 and yk. Then this is what the equation of your input output side. This is what the equation for the output side. So you will see that you will obtain a polynomial in the input side, output side. In the same way, you can write this polynomial as QE, the polynomial of E in output side. Similarly, we will have a polynomial in the input side. That polynomial is represented by PE in the same way we have written this thing. Now, if we want to, after having the thing written in this form, what you can do, you can proceed with solving our difference equation. So I will illustrate it in the next class, inshallah. So at this stage, I want to share one thing with you because our mid-exam is appearing. We will be giving you a guideline letter because we have something circulated today from VC's office. I have to understand that thing first, then I will give you my understanding to you, okay? Then we will discuss about the format of our mid-exam. But meanwhile, I want to take another mock test using IoT LMS. I will be sharing one thing to you. It will also be a mock test, but your mock test will be I don't know where it is. Okay, let me find it out. Okay, I'm sorry, it is not appearing. Probably network is creating problem. Okay, can you see this page?
Yes, sir.
Yes, sir.
Okay, then your quiz will be appearing in this way. Okay, you see that a question will be appearing there. Okay, let me again start from the beginning. Okay, your question will be appearing in this way, okay? For example, say question 1. Your question 1 will be appearing in this way. What you need to do, you do not go to the next page, okay? You solve your question to your paper, then you scan it to a PDF file. Once your file is ready, then you go to next, okay? Can you follow me?
Yes, sir.
So once you have this thing, another issue is that if multiple attempt is allowed, in the next attempt, those data will change. So your solution will not be valid. For this reason, our attempt will be restricted to one, but time will be given there. So what you 20 minutes for each question. So once your question is solved, you take your photograph or everything you need. Then after having this thing ready to you, you go to your next page. You will see that your next page will appear in this way. Okay, you need not to answer this question. What you need to do, you just upload the files that you have solved in your previous case. Okay, once your upload is complete, then you go to your next page. When you will go your next page, your next problem will be appearing. then you do not answer here, okay? What you need to do, you keep the thing in your screen and try to solve your problem. After your solution is complete, then you again go to the next page. When you will going, you will be
Excuse me,
going to
sir.
the next, yeah?
Sir, by not answering, do you mean that we do not select the options?
You do not need to select the options because those options will be invalid. The reason is it is your written exam. Okay.
Yes,
Okay,
sir.
sir.
So for this
Yes, sir.
reason, if you put some options there or even no there, that will have no effect. Okay. Because I will examine by using your uploaded file. So
Okay, sir.
forget about answering there in the book, okay? In the question, but you have to upload the thing. In this way, you will finish. No shuffling will be there. But if multiple attempt is allowed, the one problem is there. If you submit mistakenly and again go back, then your data will change, and you have to again give the solution with your changed data. Okay. For this reason, my advice is you just keep your question displayed. Then you solve the thing, then you prepare your doc, then you upload to your next page. Okay, in this way you can finish your exam. I don't know how your LMS will be performing. If I want to take the exam by using LMS, I will be using IUT LMS. For this reason, tomorrow from 6 p.m. you will have a mock test. This quiz will be given as a mock. Okay, I want that every student should participate in the mock. Those who will not participate, that they will be penalized. Because I
Yes,
need to
sir.
know that IUT LMS is working, because I have the feedback that it is working well, others are using. So that is what
Yes, sir.
from my part today. Let me give you percentage. Okay, you have a class probably after this class, isn't it?
Yes, sir.
So we have to be a bit fast. Okay, so 35.
Yes, sir.